Hi everybody, my topic is about the evolution of pore structure and cyclic loading and its effect on recurrent liquefaction. It is generally believed that sand consolidates after liquefaction following the dissipation of excess pore water pressure. However, in the Nihonkai Chubu earthquake, 1983, the main shock hit Omori with a magnitude of 7.7 and the acceleration of 2.78 meters per second square. It caused a large area liquefaction. 1 month later, the aftershock hit the same site with a magnitude of 7.1 magnitude and a much smaller acceleration 1.09. However, it caused liquefaction again. The same phenomenon also happened in New Zealand and California. Today I'm trying to give an explanation for this phenomenon, recurrent liquefaction, from the microstructure of voids. Firstly, let's take a review of the mechanism of liquefaction. When a loose granular soil is saturated, or the void space is filled with water, after the loading is applied, particles want to pack more closely, but they need to push the water out. If the loading is slight or is applied slowly, the water will drain out and allow the particles to get closer together, so the settlement will happen. But if the loading is strong and applied quickly or repeatedly, such as an earthquake, the water cannot drain out fast enough to make room for particles as they try to. At this situation, the pore water pressure will increase. When the saturated sand subjected cyclic load, the pore water pressure will accumulate as the number of cycles increase. We can sketch this process as this picture. When the pore pressure equal to the total stress, the liquefaction will happen. So now from the mechanism of liquefaction, we know that voids play a very important role in liquefaction. So here is the question. What happened on voids during the first liquefaction, and how will it lead to the recurrent liquefaction? In previous studies, some factors have been considered. Emery noticed that a loose layer is formed on the top of the specimen after liquefaction test, so she conducted a series test to check the uniformity of voids. The result is here. These two samples were prepared without shaking. The distribution of voids was uniform. Number 15.3 and number 16 samples liquefied once the void ratio of the top and the bottom is larger than the void ratio of the medium part. Now, what's the relation between non-uniform distribution of voids and liquefaction resistance? In order to get the relation, a laboratory test was conducted by Oda. He mixed loose layers with dense layers to create non-uniform distribution voids. The test results shows the liquefaction resistance of non-uniform specimens are slightly lower than the uniform specimens with the same relative density, but the reduction is minor. It cannot be used to explain the drastic reduction of reliquefaction resistance. The second factor should be considered is the strain. For a small strain, there is low change in the fabric and there is low excess pore water pressure, so in the theory, it will not affect the liquefaction resistance. Test shows sometimes the small strain will increase the liquefaction resistance slightly. It can be explained by the small strain changed some unstable microstructure. The rise of excess pore water pressure can be depressed in the subsequent liquefaction test. For a large strain, the microstructure will be totally changed. The result shows that the large strain changes the liquefaction resistance a lot. This is because large strain will create an allotropic unstable structure. Because of the action of gravity, all lateral sands are allotropic. External loading will intensify the allotropy. Most of the load in particulate materials is transferred through the load-carrying chains. Other particles play the secondary role of preventing the chains from buckling. In the right picture, the black circles denote particles stressed more than the average. The white ones denote particles stressed more than half of the average, but less than the average. It shows that the highly stressed particles are linked in series, and they tend to align parallel to the compression direction. I used the yellow lines to highlight these load-carrying chains. There are two ways to form the columnar structure. The first one is create new contact in the principal stress direction. The second method is to lose contacts in other direction. Actually, particles choose the second one. This is the experiment proved the contact loss. The left picture is the device. The right picture shows the contact loss when load applied. This kind of contact loss will not recover after unloading. This picture is the contact area after unloading. So, because of the contact loss, large collected voids will form between columnar structures. It is extremely unstable when it is stressed perpendicular to the elongation direction, and the forward pressure might be sharply raised when it is cyclically stressed. So finally, this is my conjecture. During the previous earthquake, an allotropic and unstable columnar structure was formed. When the earthquake stopped, the columnar structure remained. Aftershock coming from a different direction because of the unstable structure, voids will close, excess forward pressure are sharply raised. Under the cyclic loading, the excess forward pressure in the first cycle controls the excess forward pressure in the second cycle, and the second one controls the next one. So finally, recurrent liquefaction happens. That's all. Thank you for your listening.